Welcome back. So now let's look at a modified Atwood's machine. So in this problem we have a mass 1 that's on a table and mass 2 hanging off a table, and again we have our little magic frictionless massless pulley right here in between, and there's a string that connects M1 and M2. We're given the masses, we're given the coefficient of kinetic friction between M1 and the table is 0.2, and we're given that the magnitudes of all the forces acting on M1 and M2, we're given that. We're asked to find the magnitude of all the forces acting on M1 and M2, and what is the acceleration of the boxes. So, since this is a force problem, what do you suppose the first thing that we should do is? You're right, we gotta draw free body diagrams. Okay, so we'll draw one for mass 1, we'll draw one for mass 2. So start with our dots, dot, 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 and we will put mass 1 has a very large weight by the earth on 1, and mass 2 has a smaller weight by the earth on 2. There's only the string holding up mass 2, so tension, and again just like before we'll just call it tension because it's the same tension in the string for mass 1 and mass 2. The acceleration of mass 2 box is down, and the acceleration for mass 1 is going to accelerate this way. So the acceleration is not equal because they don't have the same direction, but they will have the same magnitude. So just as a reminder, the acceleration for box 2 is down, so I'll just bubble that here. And the acceleration for box 1 is to the right. I'll bubble that there. Okay. And now let's go back to black pen. Alright, so we have the normal by the table pushing up, so normal by the table on 1. We have the tension pulling this way, and then we have itty bitty little friction. It has to be smaller than the tension by the table on 1, going that way. Okay, so we could solve for a couple things pretty easily. Let's solve for the weight. We can solve for the weights pretty easily. For mass 2, I got this mixed up over here. I want the larger, well, it doesn't matter, we could just say that. Mass, well no, because this one is drawn bigger, so let's make mass 1 10 kilograms and mass 2 5 kilograms. That's what I meant to do and I wrote it backwards. Whoops. Okay, so mass 2, so this weight would be 50 newtons, and this weight will equal 100 newtons. Okay, so that means this normal is 100 newtons right there because they're balanced in the y direction. If we solve for the friction, we could use that fun equation, right? F equals mu n. So friction is equal to, I think it's 0.2. Let me double check that. Yep. 0.2 times that normal, which is 100. So the friction is equal to 20 newtons. I'll put that right there. Okay. Now we're at a spot where we could write our F net equations. So let's get a different color pen here. We could get purple. Okay, so I'll write it for mass 1. Sum of the forces for 1 is equal to mass 1a. Since the acceleration's to the right, we'll go the tension minus friction is equal to m1a. We don't know tension, but friction's 20, so T minus 20, M1 is 10, and we don't know acceleration. Now we do the equation for mass 2. Sum of the forces for 2 is equal to m2a. So sum of the forces, since the acceleration is down, we do what's going down, which is the weight, minus what's going up, which is the tension, equals m2a. So the weight's 50 minus tension equals m2 is 5a. And then just like before, we'll stack the equations. So t minus 20 equals 10a, and negative t plus 50 equals 5a. T's cancel out, so 30 is equal to 15a. 30, so 2 meters per second squared is equal to a. Okay, and then if we want to solve for the tension, we can plug it back into one of the equations. Doesn't matter which one. So let's see, t minus 20 is equal to 10, and the acceleration is 2. So t minus 20 is equal to 20. So t is equal to 40 newtons. And then we could check with plugging into the other equation. So 50 minus t is equal to 5a, which is 2, right? So 50 minus t is equal to 10. And so 40 newtons is equal to t. Very good. Excellent. So there we go. Let's see this. What does that do? Excellent. So we did our free body diagrams to begin with. We noticed where the accelerations are, and I put that in green. We solved for our friction, wrote our F-net equations. Notice that from here to here, there's no physics. There's no physics equations or anything. This is just algebra. It's just plugging and chugging and solving for variables. The physics comes in right here in your F-net equations, right there, and right here. And also very, very much so in your free body diagrams that really just guide you in developing and forming these F-net equations. So I hope this helps. We're going to have so much fun in class, and I can't wait to see you and do some more physics with you. So I hope you have a great night. Bye-bye.